Greetings, ladies and gentlemen. I am Professor Valdemar, and I'm going to present my talk entitled Experience and Challenges on Modeling and Simulation of Systems Software Architectures. Well, for me, it's an honor being here. I was really glad about the invitation since I have been part of the SESoS WDES for years, publishing papers and also in the technical program committee. So I was really glad and I really appreciate the invitation. Uh, Thank you, Everton, Rafael, and Jan. And so let's go. Well, for my presentation, I want to introduce myself with a brief presentation. I want to provide you some context and definitions that are important for this talk. After that, present the state of the art and practice experience on modeling and simulation for SESoS software architectures, some cases and challenges that still remain. Well, as you know, I live in Brazil, and Brazil is really huge. And when we think about Brazil, it's natural that what comes to our minds is about Rio de Janeiro and samba and all these feelings that Brazil transmit when it comes to our minds. But actually, I live quite far from this reality. I live here in Goiânia. It's in the state of Goiás, and it's actually close to Brasilia, which is the capital in Brazil. But well, we are far from Rio, but it's possible to go there by plane. And this is the building where I work. Of course, not now, since we are living the pandemic, and so we are working in home office. But this is the Informatics Institute in the Federal University of Goiás, and here is where I intend to come back to work when all this passes over. Here I have established a research team. It's named Go Inside. Here you can access our website and you can see details about the visits we have received and the papers my group has published and all the projects we have been involved in our partnerships and collaborations as well. So my talk, when we look at the title, there are some important concepts that I need to introduce to make you all comfortable to understand where we are and we are in to be in the same page. So the concepts are systems of systems, software architecture, systems of systems software architectures, the combination of both the first and second topic, and modeling and simulation. When we think about systems of systems, and well, this is the main topic of my research, and that's the reason why I'm here. This is one of the main topics of this workshop. And systems of systems are an alliance formed by independent software-intensive systems called constituents that interoperate to achieve common goals. One main example of systems of systems are the smart cities. Is the idea that you have many different and independent systems that work together to achieve more complex goals. For example, we can think about the smart traffic that are formed by many autonomous cars and the smart the traffic lights and the crosswalk and all the idea of smart cities is that all of those components have much software, and so it's possible for them to intercommunicate and coordinate to offer more interesting behaviors. So that's the idea. Actually, the systems have received software to become smarter, and the systems have been interconnected. Here we have two examples. Here we have several autonomous cars intercommunicating to offer behaviors that they could not deliver isolately, but in combination they can offer can offer them. For instance, avoiding collisions, offering a fluid traffic over the road. So these are examples of behaviors. Here we have a Brazilian example, not exactly. Now we are not still dealing with drones to deliver food, but well, this is the what we glimpse for the next years. It's the idea that, for example, if you think about a pizzeria, and the pizzeria has an information system, so you in your mobiles you have apps that enable you to ask to order some food, and you have a drone to deliver the food. The idea here, this can be understood as a system of system because all of those systems are independent. A drone, for example, it's not exclusive for this type of situation. It can be used for many other purposes as well. But it's only possible to deliver this type of behavior, like delivering food, because of the combination of the capabilities offered by all of those systems. Any one of them isolatedly could deliver the food, but they working together, they can deliver the food. That's the idea. Actually, when we think about systems of systems, this is not actually such a weird idea because we ourselves, we are systems of systems. When we think about us, we are formed by many different systems, such as the digestive systems, the system, respiratory system, nervous system, circulatory system, and actually those systems interoperate, and this is fantastic. For example, when we breathe and the air comes inside our lungs, the oxygen is collected by the respiratory system and delivered to the circulatory system. The same occurs when we think about the digestive system and the circulatory system. The nutrients that that come from the food, they are delivered in the circulatory system as well. And so this is the dynamics of different and independent systems that interoperate to deliver more important behaviors, such as your life. So systems of systems have emerged as the result of the need to interoperate the systems, and they have important characteristics. For instance, the operational and managerial independence of constituent systems. This means that the systems they can work inside the context of the SESoS or outside of the SESoS. So they are not exclusively dedicated to the system of systems. They can contribute to the system of systems, but they are not exclusive to the system of systems. So the constituents can join and leave the SESoS at runtime. That's the idea. And managerial independence, it's related to the fact that many companies or people can own they can hold possession over the constituent systems. Actually, the system of systems are designed or they are planned to offer emergent behaviors. These are the behaviors that can be designed, that can be engineered as the result of the combination of the capabilities offered by the individual constituents. So we can draw bigger behaviors as the result of the individual capabilities offered by the constituent systems. Dynamic or evolutionary architectures, because the architectures, they are the result of the combination of the constituents that form the system of systems. But at the time passes, the constituents can join or leave the SESoS. So this results in a overall architecture that changes over time, and distribution, since we need to have some network technology to enable the communication between the constituent systems. So this is the idea. Each architectural arrangement SESoS can assume, we call them arrangement or coalition. And this is the idea of devolutionary architecture. When we think about a first coalition formed by systems 1, 2, and 3, and you have a fourth system that comes and join the SESoS, this has changed the entire architecture of the SESoS, and so we have a second version of this coalition, and this is why we can we can observe the evolutionary architecture. But actually, if you think, this can highly impact on the behaviors being delivered, because if a constituent joins the SESoS, so virtually we have some more capabilities that can be used to be combined and offer more robust behaviors. But if some critical constituent goes out or leaves the SESoS, so maybe some important behaviors being delivered by the entire SESoS can also be harmed, or even they can become unfeasible. Another important concept in systems of systems is about goals and missions. Actually, mission was a term that comes from the military domain, and this happened because systems of systems were really common, firstly, in the military domain. Here we have an example of a kind of mission in the military domain, for instance, Saving Private Ryan. But now we have a reality where the systems of systems are coming to the civilian world, and so mission can sound a little bit weird, and that's the reason why we have over the years, not only me and my contributors and partners in research have renamed mission and call it goal. So a goal, it's the idea of an activity that can be partitioned into smaller operational tasks and assigned to constituents with matching capabilities. So it's the idea that for offering some behavior as delivering pizza, we need to split this activity in a process that have different parts, and those parts must be assigned to the constituents that has the capabilities, such as deliver the pizza, produce the pizza, order pizza, and the combination of all of them will make up the goal, the entire goal that is delivered as an emergent behavior. Okay, so systems of systems, or SESoS, I will call it SESoS during the talk interchangeably. Besides SESoS, we also deal with software architecture. But what is a software architecture? Software architecture is understood as the backbone of any well-succeeded software product. And in general, it is formed by the structure, behavior, and the description of the environment. When we think about the structure, we are dealing with the main parts and how they are connected, the behaviors being delivered by the architecture, and the environment. In general, software architectures are designed to achieve quality attributes or ELITs, such as reliability, availability, security, and performance, and other quality attributes, of course. And in general, we represent the software architecture using some architectural representation or description. And in general, we use architectural views that, in general, also we use UML and SysML to specify them. So, but combining both the topics, SOS and software architecture, we achieve what we understand as the systems of systems software architectures. So when we think about the software architecture, if software architecture is structure plus behavior plus environment, a SOS software architecture is the same structure, behavior, and environment. But when we think about the structure, we are talking about the constituents software elements plus the interoperability links that enable the communication between the constituents, plus the behaviors, plus the environment. TOS has a dynamic or evolutionary architecture, and software engineering uses static notations. In general, software engineering, we use SysML or UML to represent the architectures, but how could we use static notations to represent something that is essentially dynamic? So that's the problem, that we identified some limitations of UML and SysML. In general, those both languages that are the most common language in software engineering, they represent single systems, not multiple systems as we are doing here. They are static notations, and we need something to represent the dynamics of the system. And the architectural evolutions inherently outdate the documentation. This means that, for example, we have we decide that we want to represent the constituents, each constituent using UML and SysML. But if a new constituent comes, so the architectural description is already outdated automatically. And we can use UML and SysML, maybe using stereotype or maybe adapting it to represent the constituents and the interoperability links. But the idea here is that it's still static, and we need to do adaptations. The languages are not they are not able to natively represent the system of the system. And that's the problem. It's because the SOS software architectures require executable notations and models. It's important that we have precision, because sometimes we are dealing with critical domains, and if some essential critical constituent leaves the SOS, this can maybe cause deaths and losses and financial losses or injuries. So we really need to assure precision in representation to avoid these situations. Formalism to deal with complexity, because systems of systems in general are complex. They involve several constituents and links, so it's really hard to glimpse the entire picture, and so models can really help. It's important that we have some formal basis for verification and validation, because of the precision and because of the critical domains that are often supported. The reliability in representation is really important. It's important to represent structure and behavior and the surrounding environment. And it's important to offer a prediction of the properties at design time, since we need to plan it for the runtime. So, we have the conclusion that we need executable models to represent dynamic or evolutionary SOS architectures. But which ones? Well, we have some options. We have models at runtime, such as the GEMOC technology or executable UML. We have digital twins, and we have simulation models. In our case, we decided to use simulation models because particularly devs, they have some characteristics that were closer to what we have as requirements for representing SOS. And devs, for instance, offers some formal definition, Java-based tools, but if you want to use Python as well, we also have some free tools to use. Match with SOS, the SOS software architecture represents requirements such as being executable, being visual, enabling to represent multiple systems and the data exchange, and many other advantages. But what exactly is a simulation? And so here we arrive in the last point of our concepts for background is about what is modeling and simulation. When we think about simulation, a simulation is actually the imitation of the operation of a real world process or system over time. And the simulation is performing some goal directed experiments with models of dynamic systems. More than simulation, every time we need to simulate something, we need to draw a model. And so we need to work with modeling and simulation, or modeling for simulation. And the act of simulating something first requires a model to be developed. And that's the reason why we used to call it MNS. We have some examples of simulation formalisms and techniques, such as MATLAB, that is really recognized by the scientific community, DEVs, systems dynamics, multi-agent-based simulation with some important notations and frameworks such as JAD and NetLogo, and Faro. This is a recent tool from the Fraunhofer Institute. In that context, we already have some work done on simulation in the context of software engineering. I want to highlight here two important works I am aware of. The Breno France's work. He has invested on software engineering using simulation, and he has published, among other studies, one is a systematic mapping on the simulation practices in software engineering. He has concluded that the most used formalisms for software engineering are systems dynamics and devs. And he also has proposed some guidelines on how to use simulation models for software engineering. And this is really nice for experimentation, the evidence-based software engineering purposes. And Veronica Bogado has exactly used devs for simulating the analysis for conducting the analysis of software quality attributes, and for representing software architectures using devs and proceeding with quality evaluation. So here is an example that I want to show you, so you can familiarize yourselves with the devs notation. In the beginning of my research, I have produced this video, and we have represented a real flood monitoring system. The idea that this is delivered in São Carlos, São Paulo, and there is a river that crosses the city, and we have some smart sensors deployed on the board of the river, and they collect the flood level and forwards it using mediators until a gateway. If a gateway detects that some threshold is transpassed, so it triggers a flood alert. So this is the idea. We have used MS for Me tool. It was an implementation for devs. Actually, it's created by the devs creator, um, and and it represents with atomic models represent the systems and coupled models represent the entire architecture, and so we could simulate this flawed monitoring source. Okay, the problem is because as was perceived in the presentation, devs is based on state machine sports events and in that in animation. But in general, software engineers, we don't like these notations. We prefer the third generation languages. And by the way, to confirm this hypothesis, we have conducted, me and my students have conducted a survey here in Brazil about the using devs for solving problems. And the idea is that we expose some software engineers for using devs for solving some problem in their everyday life. We have 58 participants, 44 from Brazil, 14 from other countries, among them 28 from academy and 30 from industry. And actually, we have some positive findings because the visual appeal allow to predict characteristics as design time. It's easier to include new members. It can help with architectural assessment. But the software engineers, they didn't like the lack of possibility of changing colors, or the animation was not that pleasant for them. So our idea was, okay, so let's bridge the gap and gather both worlds and combine software engineering notations with executable simulation. The idea is establishing a synergy between modeling and simulation, because software engineering can help to increase the level of abstraction of simulation and can help the automatic generation of code for simulation, while the simulation can enable to predict properties at design time for the systems developed by software engineering. So the idea we established was converting, automatically mapping software engineering static notation. Was the SESoS ADL was an architectural description language proposed at that time for systems of systems, and converting it for executable simulation model in devs. So the first idea was this one. We had some systems of systems specified in SESoS ADL models using Xtext. We had an extend script to automatically convert it for devs models. The devs models were deployed in simulation platform, the MS for Me, and so we could see the SESoS simulation emerging. All of these infrastructure was based on Eclipse modeling framework. Problem is because we also needed to represent the environment, as we saw in the definition of SESoS software architectures. And so we proposed the stimuli generator. We could automatically produce an artificial entity that could continuously feed the simulation, so it could represent the environment delivering data for the source. And we also needed to represent and manage the SESoS dynamic architectures. So we also proposed a dynamic reconfiguration controller. With that, this enabled us to study the impact of many different coalitions on the behaviors being delivered. This was quite interesting. And we also decided to use this approach for evaluation of SESoS software architectures. And so we proposed ASAS, the ASAS evaluation method, using all this infrastructure we proposed. We evaluated ASAS using a SESoS, and this was a partnership we could count on the Brazilian Institute for Space Research and the University of São Paulo. And the idea is launching satellites can be really expensive, and so we cannot only launch a satellite and with no reasons or rational or not being sure that this can be really successful, or this can bring important advantages. So how to have an estimation about if the acquisition of new satellites that are really expensive could improve the actual service. So the context here is that in the Brazilian space source, we have really isolated places, and the environmental conditions of those places are collected by local data collection platforms with what we call DCP. And when the satellite flies over the DCP, the data collector is uploaded and it flies over Earth. And when it arrives in São Paulo, where we have a treatment center, the data is downloaded, and so uh, it can be treated and disseminated for the scientific community and for meteorological predictions. So we simulated two missions or goals to perform the environmental data collection and to obtain pictures from the Amazon region using the satellite. And the aim was to evaluate how to increase the increase in the number of satellites from 1 to 6 would influence on the level of research competition between the the data collection platforms uploading data and the pictures that needed to be obtained, the percentage of goals met, and the impact of the number of satellites on the SESoS performance as a whole. We have obtained data from the Brazilian Space Institute. The period analyzed was between January and October 2017, and we simulated each data collection platform station in operation in the entire Brazilian territory. These achieved a number of more than 300 constituents automatically generated and being simulated, and these took 34 hours of simulation. We concluded that an increasing in the number of satellites could really reduce the competition between the constituents. So this could justify the acquisition of new satellites by the Brazilian government, and this reduced data losses. But besides space SESoS, we also have worked on other simulations. We have worked on flood monitoring, smart building. We analyze specifically functional suitability and cost acquisition prediction for constituents. Space SESoS and the smart parking, analyzing availability. So actually, we have already generated more than 1 million lines of code of operational models in devs and simulated more than 130 hours of simulation. As contributions, we can report a combination of static and dynamic notations via model transformation, a method for evaluating SESoS software architectures, a combination of simulation models with architectural models, and the prediction of preparedness at design time for software engineering in the context of SESoS. It's because some challenges still remain, for instance, scalability. How to simulate an entire smart city that can be composed by millions of constituents. We have seen that with 300 constituents, this took 34 hours. So we have a problem in scalability in two dimensions. One, processing, because how to process millions of constituents in those simulations. So we need to use maybe parallel processing, multi-core processing, and probably distributed simulation. And the problem of visualization perspective, how to visualize millions of constituents interoperating. So this is something that we still need to study. How to assure an entire set of quality attributes. Until now, we have invested on specific quality attributes, but we didn't have a simulation model that really could address an entire set of quality attributes. So how to do it? Coverage. We saw that SOS can assume many architectural arrangements. So how to have a good coverage about how to test all the combinations of coalitions a SOS can assume, how to make the simulation formalisms and animation more software engineering like, and about the simulation education and training, because well, we have some partnerships now with the Fraunhofer Institute in Germany, and we have perceived that for specifying a really reliable simulation for critical systems in general, the software engineering is not enough, and even the systems engineers have not been capacitated for this endeavor. And so we actually need nowadays a multi-professional team with mathematicians, physicians, software engineers, electrical engineers, and other specialties of engineering. And so we need to draw a simulation education and training program to cover all the abilities that are really required to specify really reliable simulations. Before finishing, I want to show you that we are conducting the third the third edition of our workshop on modeling and simulation of software intensive systems, the MSIS. The deadline is arriving. It will be on June 14th, and it would be really nice if we could receive some papers of yours. We also have a tutorial accepted in EXA, the European Conference on Software Architecture. This will take place on September 13th. And this is the link, and it's entitled Simulation of Software Architectures of Smart Ecosystems, Theory and Practice. So you are really welcome to join us in that tutorial as well. And I am available here for questions. I really appreciate your audience, your attention, and thank you very much.